everyone! This summer I've been taking deep learning through Harvard DCE, and today I would like to present my final project for the course. The first part of this video is going to be the Python implementation that I did in Google Colab, and the second part of the video is going to be how I implemented it in Rust. So for the grading staff, you can end the video after the Python part, as that's the only part that's going to be relevant for you. And for those who are here for your usual dose of Rust, it will happen, I promise. It's just worth understanding the Python project first. Given that I used to work in institutional FX trading, I chose to do a case study in finance, specifically Euro-dollar directional and volatility forecasting with LSTM networks. So the premise for the whole project was, can a neural network predict which way the exchange rate is going to move in the next hour? And just to speak a little bit more about my motivation, I spent 10 plus years in fintech working on production trading systems. My specialty was FX, so I worked in retail FX before moving to institutional trading. So I have a lot of familiarity with the data and experience in reading candlestick charts, market terminology, that sort of thing. And really good historical Euro-dollar data was actually readily available on Kaggle. The data is from a retail FX broker called Oanda. The zip file of this data also provided minute and news data, but I didn't really need that for this project, so I just disregarded those two CSVs. The main one that I used was Euro-dollar hour CSV. So if you're not familiar how FX trading works, you basically have the bid price and then you have the ask price. Bid is basically the highest price that a buyer is going to pay, and then ask is the lowest price that a seller is going to accept. And the spread between the bid and ask is usually the commission that you pay to enter the trade. And in the FX industry, that's usually priced in pips. Just to go through the main columns in this data, you have the date, you have the time. So the time is actually going to be the hour in which the price was measured. Then you have the opening bid price and the highest bid price. And you have the lowest bid price and the closing bid price. You have BCH, which is the change between the open and close price. You have the opening ask price. You have the highest ask price and the lowest ask price. You also have the ask close, and then you have the ask change. So the change in the ask close price from the previous period's close. To import all that into Google Colab, I just used my Kaggle API key and then downloaded it from there. So once I had it, I could put it in a data frame and I was able to start manipulating the data. So those basic columns that I had originally from the data itself were not quite enough to do all the analysis I needed, so I did some feature engineering. I took the prices that were there and I started calculating the hourly return, the spread, the RSI. If you've ever looked at a candlestick chart, you'll see indicators that traders will put on them, and one of those indicators is RSI. I did also moving averages as another indicator as well, so I calculated that and put it in its own column. Momentum and moving average ratio, and all of these are taking into consideration a 24-hour look-back window. And a standard scaler is fit only on the training split and then applied to validation and test to prevent leakage. Then I did label construction. So the binary label here is, does the next hour's mid-close go up or down? And up is going to be a 1, and then down will be 0. And then I also had the deadband. So I spoke a little bit about spread earlier. You pay the spread when you enter a trade. And again, that's the difference between the bid price and the ask price. And most 1-hour moves are actually smaller than this spread. So therefore, entering the trade is not really going to be profitable for you because you paid this spread and you didn't really make it up. So the only moves that need to be flagged here, because again, we're looking for profitable moves, are the ones where the size of the move exceeds the relative spread. The next part was actually building the sliding windows. The data frame originally was just 1 row per hour, which was this flat table. But the LSTM model that I'm going to build, it needs a sequence. So each sample is created as a look-back hour window of features used to predict the next hour's direction. And the deadband also needed to be applied to ensure that only samples with moves that exceed the spread are kept. And then I had the train test split, which was a little different than usual because we're working with time series data here. So I had to be very careful not to leak future data into the training. because if you start leaking that into the training, then you automatically know what the price is going to be in the future, and that kind of defeats the whole point of predicting it. So I ended up with a 70-15-15 split. So 70% of the windows were used for training, the next 15% were used for validation, and the final 15% were used for test. The next part was feature scaling. You have other features, though they're all very different scales. So RSI is between 0 and 100, and return is a very small decimal usually. So the scaler is learning each feature's mean and standard deviation, and it's going to fit on train only to avoid leaking information about the feature into the model, because remember last slide, that was a little bit of a problem at first. So after scaling, reshape puts it back into the proper shape that the LSTM model is going to expect. You might be wondering why this says Model 1. I'll get to that in just a little bit, but this was the main premise of the project originally. So the question asked is, will the next hour's price be higher or lower than the current one? So this model acts as just a direction classifier, and it's a binary classifier. So again, you have two choices. You're just going to say up or down. The architecture is that I have an input layer, and then I have my LSTM layer, and then I have a dropout layer, and then two dense layers. So if you're interested in the number of parameters for this model, the count is 4 times the number of units times input dimensions plus units plus 1. And 4 is here because the LSTM cell has 4 internal gates, as we discussed in class, and so it's 4 times 32 times 13 plus 32 plus 1, which gives you 5,888, and then the dense layer, 16, adds 32 times 16 plus 16, which equals 528 weights plus biases. Then you have the dense 1 layer, and that adds 16 times 1 plus 1 equals 17. So all in total, you have 5,888 from the original LSTM layer, then you have 528 being added on by the dense 16 layer, and then you have 17 being added on with the dense 1 layer. So that gives you 6,433 parameters. The next part was training. So there's 2 callbacks. So I have reduced LR on plateau, and that halves the learning rate if value loss stalls for 2 epochs. And then I have early stopping, which was suggested a few times, so I decided to try it here. Early stopping stops training if value loss hasn't improved in 5 epochs, and just restores the best performing weights, not just the last ones. So the early stopping consistently occurred here between 10 to 19 epochs, meaning that the model plateaued pretty fast rather than needing the full budget. The results here were less than ideal, which is actually to be expected, and I'll explain why in a second. So euro-dollar direction accuracy only worked out to be around 50%, which was pretty much random guessing. So is the market going to go up or down? Is pretty much 50% chance of getting that question right. Yet the model didn't really overfit, so training loss stayed close to LN2. But why is the bad results? This aligns well with the weak form efficient market hypothesis, which states that all information contained in past market data is already incorporated into the current price. So predictable patterns that are based solely on historical prices just can't be exploited consistently to obtain abnormal returns. And also notice here that we're not correlating the euro-dollar price movement with anything else, so we're not correlating it with that of any other currency pair, such as dollar-yen, and we're not correlating it with any individual stock movement or index fund movement. So perhaps if we did that, there may be a better chance of pulling out some sort of correlation. So then I asked, how can I get a higher performing model out of this? What about predicting volatility instead? Because large moves tend to follow large moves. I was around when the Swiss franc was unpegged from the euro. And here I did a log transform because volatility is strictly positive and right skewed. And then I added 8 volatility-specific features. So here's architecture for the second model, where I was aiming to predict volatility, not price movement. The architecture was actually very similar to Model 1. You'll see this commented outline here. I tried to go with 64 units, and then I plotted training versus validation loss, but I got a pretty bad overfitting. So I just went back 32. So I have that LSTM layer, the dropout layer, a dense 32 layer, dropout, and then a dense 1. So you'll notice the dense 32 is a little bit different from the dense 16 I used earlier. And then when I called the compile function, I used the atom optimizer and MSE loss. So this trained for a little bit. Originally I used the batch size of 256, but I went to 512 to get a little bit better results. And I also had the early stopping on this as well. So Model 2 actually performed much better. And again, we're predicting volatility here instead of trying to predict the price movement. Predicting volatility came out to have an 82% accuracy. And I compared this to a lot of the benchmarks that are used in the industry. You'll see a little bit more of that in my report. But this was much better than the direction baseline by about 30%. So this model actually performed very well when it came to predicting volatility. And all in all, I was glad to get a more positive result out of this. Of course, 82% accuracy is nowhere near perfect, but it is a lot better than 50% accuracy of trying to predict the price. So yeah, that covers the Python version of the project. Now I'm going to transition over to how I implemented this in Rust. So in the past, I've used Burn. I've built a CNN model with Burn using fashion MNIST data, and then I've also built a linear regression model with Burn, but I had never done an LSTM model in Burn, so I decided to go ahead and tackle that here. And if you're not familiar with what an LSTM is, LSTM stands for long short-term memory, and it's a type of recurrent neural network that's designed to work with sequences and remember useful information over many time steps. So instead of doing both models, I already knew that the price prediction forecasting really wasn't going to give anything valuable, so I decided to only do the volatility forecasting model in Rust. So all in all, the pipeline is 6 files. You have Kaggle RS, which gets the raw data into disk. You have features RS, which turns the raw price bars into 21 engineered features. And then you have dataset RS, which slices features into 24-hour sliding windows, scales them, and splits them into train, validation, and test. Next is model RS. That's the actual LSTM model architecture itself. And then you have train RS, which is where the training loop resides. And the last file is eval RS. That's going to score the predictions against the baselines and print that report I was talking about. So main RS just calls these 6 in order. So stage 1 is Kaggle RS. This is the entry point that main RS calls first. It's going to check in the data folder, do we have Eurodollar hour CSV? And if we don't, it's going to basically read the env file for the Kaggle token. It's going to hit the Kaggle API for the dataset and then download it. But sometimes Kaggle replies with the zip and sometimes it's the raw CSV. So the code sniffs out the first 4 bytes for PK0304, which is the magic number for a zip file, and then it unzips it if it is a zip file. Otherwise, it's just going to copy that file straight through. The next result of this stage is basically we have our CSV. It's got the hourly Eurodollar bid ask, open, high, low, close bars sitting in it, and that's all we needed from Kaggle RS. Stage 2 is features RS. So this is building that features table. And it's a line-for-line port of the Pandas feature pipeline, and Pandas has a lot of subtle rolling window and non-handling behavior that has to be reproduced exactly for the numbers to match the original notebook. You have the function build CSV path volume frame. This is the basic entry point. It calls read bars and then the engineer. And read bars parses the CSV, pulls out date time, and then the 4 bid columns, which is bid open, bid high, bid low, bid close, and then the 4 ask columns, which is ask open, ask high, ask low, and ask close. And it sorts everything chronologically by the timestamp. The raw file should actually already be sorted, by the way, but this just guarantees it. Then you have the engineer function, and this is where those 21 features get computed. So first, it collapses the bid ask into one single mid-price open, high, low, close. Again, when you're doing this, you're just basically adding the bid and the ask divided by 2. That's the pattern. So open, bid, ask divided by 2, high, bid, ask divided by 2, and so on and so forth. The spread is just the difference between the ask and the bid. So ask minus bid, that gives you the spread. Then you have the 13 shared features. The return, which is the 1 hour % change in close, the relative spread, RSI, which stands for relative strength index, and again, that's an indicator you'll see on some traders' charts, momentum, 3 hour, percent change in close, the high minus the low divided by the close minus the open divided by the closed versus the 6-hour and 24-hour moving averages. Then I have the short moving average and the long moving average. Again, those are indicators you'll see on traders' charts. Then I have the hour sine, cosine, the day of week sine, cosine, which are those cyclical encodings of the hour of the day and day of the week. Sine, cosine of angles, so midnight and 11 p.m. are close instead of far apart numerically. Then it does the first drop in a pass. So any row where one of those 13 features is none, it just gets dropped. And it also adds an extra trailing row, so that's a quirk that was carried over intentionally from the notebook, because the notebook computed its volatility features after that trim. Skipping that would shift every downstream split boundary, so it's reproduced on purpose here. Then I have 8 more volatility features that get computed on the cleaned up rows. So the end result is going to be a flat array of N features, so 21 features again, plus the future volume target and the raw return series. And that's going to land on a little over 93,000 usable rows. Stage 3 is the data set. So this is the windowing, the scaling, and the splitting. This takes the flat feature table that we got from stage 2, and it turns it into something that the LSTM model can actually train on, which is a sliding 24-hour window. So I have the window count, which is in rows minus look back, and again, look back is 24 hours. Then I have the chronological 70-15-15 split into train, validation, and test. And that's chronological because you can't shuffle time series data across the split, or you're going to leak future information into the training. Next, the targets get log transformed, which again is friendlier for the MSE-based training. Next, you have where 2 separate scalars get fit, both only on the training data. You have fit feature scalar, which standardizes the 21 input features, and then you have standardized params, which standardizes the log target. Next are the 2 baselines. So you have persistence, which gets built as kind of like that naive baseline, which predicts that the next 6 hours are going to look exactly like whatever the past 6 hours look like. And then you have the EWMA baseline. Dataset also exposes the batch function, which pulls out a tensor of the correct shape for a set of window indices, and this is actually what gets fed into the LSTM. Then you have targets. That's the matching scaled target tensor. And then you have invert, which undoes the log and standardized transform, turning this raw model output back into an actual volatility number. For stage 4, I have the actual model. So the architecture is ported straight over from the notebook. Again, apples to apples here. So we have that LSTM layer of 32. We have a dropout layer of 0.3. Dense layer of 32 using ReLU, then a dropout layer using 0.2, and then dense layer using 1. So one thing to point out here is the very slight difference in the number of parameters. So this burn version has 8,129 parameters, while the Keras version had 8,001. And burn just puts a bias on the recurrent transform as well as the input transform. So that's 128 extra parameters. Stage 5 is train RS, and that's the training loop. So for train RS, per epoch, you shuffle the training window indices with seeded standard RNG, and that matches Keras's default per epoch shuffle behavior. Then you walk in batches of 512. So forward pass predictions, you have MSE loss plus the L2 penalty from model RS. Then you have MAE tracked alongside reporting, not used in the loss. Then you have the backwards pass and the atom optimizer step at the current learning rate. Then you switch the model to inference mode and you run evaluate on the validation split to get validation loss and val MAE. And then it's going to print the epoch line. So it's going to print the loss in MAE for train and validation plus the current LR. So for early stopping, if validation loss doesn't improve at all for 7 straight epochs, the training stops early and the best epochs wait, not the last epoch, are what gets returned. Then for reduce LR on plateau, if validation loss doesn't improve for more than 3 epochs, the learning rate gets halved and its own plateau counter resets. Then I have evaluate, which runs the model over a split and inference mode. And then I have predict, which is the same idea, but returns the raw scaled predictions themselves rather than aggregated error. And then I have stage 6, which is eval RS, which is scoring against those baselines. So this is where the model actually gets judged. 3 sets of errors get computed via the small errors helper: plain MAE and MSE, naive, which is again that persistence baseline, saying, hey, the next 6 hours are just going to look like the last 6 hours. EWMA, which again is the risk metrics estimated weighted moving average baseline. And then I have the model, which is the actual LSTM's predictions. Then report print dumps all of this to standard out in the format that's shown here. So this model still beats the baselines that I set out for it, so that naive persistence and EWMA, and it also hits direction accuracy. So it turned out pretty well in Rust as well. All in all, I would say this was a great experiment to do in Rust, and it really helps you understand the internals of the functions that you're using in Python. So as always, if you want to check out the code, everything is on my GitHub. And yeah, thanks for watching. Bye!